Hi, my name is George Bollendorf and I'm the marketing manager at Empower RF Systems. Let's talk about the future architecture of high-power broadband RF and microwave amplifiers. Now, let's face it, the high-powered amplifier, it's not linear. It's not as linear as we need it to be. Low power is not a problem, but when you start combining transistors to make modules, and then you lose fidelity. And then when you combine modules to make even more power, the linearity goes further into the tank. And I'm talking broadband, kilowatt, and higher power levels here. So the question is, where do the amplifier fidelity issues get solved? Well, it certainly won't be the RF device manufacturers that solve the problem. I mean, after all, linearity, it's all relative, and it's really based on and compared to the performance of a single device uncombined. So the high-powered amplifier will always be inferior to the single device. It's actually the amplifier integrator that has to deal with the performance issues of the amplifier, and does so with great effort, cost, and time. And let's take pulsed amplification for example. It's not unusual for the input pulse shape to be manipulated with an arbitrary waveform generator to be more accommodating to the amplifier transient response. And more generally, in CW applications, you'll find the integrator having added their own external control loop, typically to level the amplifier, and that consists of a dual directional coupler, power meter power sensors, a signal generator, a PC with custom software, and that's slow. So the integrator will also add, depending on the application, an external filter or switch filters. Sometimes they'll use, instead of a single broadband amp, multiple narrowband amplifiers, and sometimes you'll see, this isn't uncommon either, the amplifier being operated at much less than full rated power, so it's more in its linear range. And so if you're operating the amp at half the power, you're actually doubled the dollar per watt cost that you're paying. So what's the big win? Let's say you can knock down the second and third harmonic completely. Well, if you can do that, you can now eliminate the external filter, and that saves you money. It reduces size, it reduces weight, it increases reliability, and you actually eliminate the insertion loss from that filter, and that can be as much as 1.5 dB. So what's the big win, and why do we care? Well, let's take electronic warfare for example. With a superlinear ultra broadband amplifier, you can transmit in multiple bands. You can jam in adjacent channels, and for example, you can create a radar pulse. You can do that all simultaneous. And so that's a huge advantage in military capability, and it comes with reduced cost. Let's take test and measurement, for example, with a superlinear amplifier. You can do your testing with multi-tones and not have to worry about intermodulation distortion. This architecture I'm about to describe also has the characteristic of making a truly calibratable amplifier, and so no longer will you need the external coupler, power meter, and power sensors for your test and measurement setup. Okay, so what's the future architecture look like? Well, it's a real-time, closed-loop digital feedback system where the amplifier input and output are digitized. The error function is calculated in real time, and the inverse is applied to the input RF digitally, then converted back to analog before the amplifier stages. Now, that might not come as a surprise to some of you. You've probably seen digital pre-distortion before, but this is a little different. The digital pre-distortion that you've seen operates on the demodulated carrier on the baseband, and the goal there is to improve bit error rates. What I'm talking about is digitizing the entire RF with the goal to create a superlinear, ultra broadband, high-powered amplifier. So what kind of hardware is that going to take? From a technology standpoint, you need A to Ds and D to As that operate at gigasamples per second with 12 bits of resolution at a minimum. You'll also need interleave, and so what our modeling has shown is that with this technology, digitizing technology that's soon to be available, we'll actually be able to get equivalent sample rates of 18 gigasamples per second. And so what that'll allow us to do is operate on broadband up to 6 gigahertz. And so we call that ultra broadband digital predistortion. So when will that day come? Currently, we design and build our amplifiers with a closed-loop feedback system, and in that system, we already make available automatic gain control, automatic level control, and soon pulse shape matching. And when the A to D and D to A's become available at adequate speeds, we'll be dropping those right into our feedback loop, and I guarantee you, when we do that, we'll be the first ones to do it. So I want you to stay tuned for that. Thank you.